What they're doing is they're making some different sized circles. You need 5 big ones and 20 little ones. So if you have Play-Doh at your house, pull it out, borrow it from your little siblings, and make yourself. And then you also need some toothpicks. If you don't have Play-Doh, other things that can work are marshmallows. If you have marshmallows and toothpicks, that can also work.
And then you can eat them afterwards.
And then it's safe to eat. True. So we'll build this and then we'll tell you what they're going to do with it here in a second.
So the idea of our lesson today, everyone, okay, is last time we learned about Lewis structures. So last time you should be able to, given a formula, you should be able to translate that into a Lewis structure, which is the 2D shape. Okay? If you can't do this yet, get help on it. Because this is foundational to everything else to come. Okay, our next step is we're going to convert that into the geometry or the 3-dimensional shape. From there, we'll then convert that into things known as polarity and hybridization. Okay? But you can't go from here to these without doing the Lewis structure correctly. So if you don't know how to draw 2Ds right or need more help on that, reach out to me. I can give you more practice over fall break. I can give you more videos. There's simulations. Like, there's a lot of resources to get help with Lewis structures if you need it. Okay? So the idea of our 3D shapes is this, well, until recently, scientists haven't been able to actually see atoms, right? We actually have a microscope now that can see atoms. It's not quite what you would think in looking through a hole, but we actually can see atoms now. But way before we even could see them, there's a lot we can still know about them based off the properties that they have. So the whole idea of these 3D shapes is it's based off of what's known as the Vesper theory. Okay, this is already in your notes, so you don't need to write this down. But what Vesper stands for is the valence shell, electron, pair, repulsion. Okay. The idea of Vesper is this. When atoms bond with one another, okay, the electrons in the bonds repel one another because they're all negatively charged. So we get this weird relationship of where they're connected, but they want to be apart. It's kind of maybe like how you feel about your family, right? You're connected to your family, but sometimes you want to be as far away from them as you can. That's how these shapes form. So what I want you to do is to show you how logical this really is I want you to come up with the shapes before I show them to you with your Play-Doh. Okay. So what you're going to do is you're going to build 5 different molecules, okay, using these different stipulations, I guess. So the first one I want you to build should have, so the big ones are always for the center, and the small ones are for the outside. So the first one should have 1 big in the middle and 2 smalls on the outside. So do that now. So grab 1 of your bigs and 2 of your smalls. Toothpicks are how you connect them. The goal is that the toothpicks are as far away from each other as physically possible.
Oh no, my blueberry.
Hold it up in the air once you have your shape. If you find it's being floppy, then just stab the toothpicks in more. You might have to make something a little bigger. Okay, this one's normally the simplest, so we use it as kind of to get us going. Can I hold yours up, okay? Okay, so I think we all have, if you built something like this, you may have a smiley face because you are correct.
Yes.
Okay. Now, it might seem, give me your attention here, everybody, right? But why wouldn't a molecule that has 2 things bonded to a middle one do something like this? Yeah, because these are repelling, right? They're going to push and get as far away as they possibly can. Okay?
So now you're going to build a 3-sided, a 4-sided, a 5-sided, and a 6-sided molecule.
Oh yeah.
Does that make sense? Okay, ready, set, build. You'll get a smiley face for everyone you figure out correctly. So you need a 2-sided, a 3-sided, a 4-sided, a 5-sided, and a 6-sided. You should have enough supplies you don't have to like take any apart to make a new one. Yeah, leave them built so we have all 5 different shapes. Okay, let's take a look at their thoughts.
Yes. How come?
So if you're at home building yourself, turn off your video and try it on your
There
own.
you go. There's the 2.
Wait, this
Wait,
one.
that's the G?
Wait.
I'm overthinking that.
Oh yeah, guys.
Okay. As we talk about these 3D shapes, the goal is this. Once again, the goal is that if I give you a formula, you can tell me what it's going to look like in 3D. Now, what influences how it looks in 3D is this idea of repulsion. One of the words we're going to use often is this term called an electron domain. What does the word domain mean in general?
X.
Yeah, or in math it's like the x values because it's that area, right? Or it's a space. So electron domain refers to the space that the electrons occupy, okay? With these electron domains, they want to be as far away from each other as they can possibly be. We have 2 types of domains. We have bonding domains and non-bonding domains, okay? A bonding domain means a single, a double, or a triple bond, okay? Sorry, there's not tons of room on your paper for this. I left a little space up above. We're on the page where that starts going horizontally. But there's not tons of room. I apologize for that. Okay? And then we have non-bonding domains, which are the lone pairs. What's important to recognize here is that a single bond counts as one domain. Okay, so let's say I have, we'll draw a shape here. Okay, first off, when we count domains, we're only counting what's on the central atom. Okay, so in this molecule right here, here's my Lewis structure, I'm only looking at the nitrogen. The domains on the outside atoms are too far away to influence the shape. But these are the ones that are pushing away from each other. Okay, a single bond counts as one domain. A double bond still counts as one domain. Because even though there's more electrons, it's still in the same space. Which is why a triple bond would count as
2 domains.
also one domain.
1 domain.
Because even though there's lots of electrons, it's still just one space. Okay? So this is a domain, this is a domain, and then this is also a domain. That's the lone pair domain. So we would say that this molecule has 3 electron domains. 1, 2, 3. These domains are going to push away from each other and orient in such a way to get as far away as they physically can in 3D space. Okay? Now, as we learn these names, what I want you to hopefully recognize here is
there is a lot of logic behind the names they are given. In a sense, they're just shape names, right? So by the end, maybe not by the end of the lesson, but after practicing this, the goal is that I can just point to it and you just know its shape. Just as simple as me holding this up and saying, what is the shape of this?
Circle.
A circle, right? Same idea is I should be able to hold up some sort of molecule and you should be able to tell me its name. Now the names are a little bit more exotic sounding than circle, but there is a lot of logic behind the name. And if you see how it looks in 3D space, which is why I wanted you to build them, the names actually make a lot of sense. So I really encourage you, rather than just like straight up memorizing these names, see what they look like and match the name to it. It will really help in connecting it. It will also make the bond angle side very logical as well, okay? In your big table that we're gonna fill out though, this column right here is the main objective, if you wanna put like a star there, okay? These are like helping us understand to get there, but this is the big takeaways. You need to know these different names and what they correspond to, okay? All right, let's take a look at our first little guy here. So hold up your two-sided one again. We already kind of looked at him. So you should have a shape once again that looks like this. Okay, so we would say that this one has, I'm going to skip over here, has 2 bonding pairs and 0 non-bonding pairs. 2 domains total. The name of this shape is linear.
That's a line.
Because it literally is a line. Make sense? What would be my bond angle here? Good. And bond angle, we're measuring like toothpick to toothpick, by the way. So yeah, bond angle would be 180 degrees. I'm just going to give you like a real life example just so you can kind of compare. You're welcome to write these down or not, but just to kind of have a, versus just Play-Doh ones to know what it looked like. So an example of a linear thing would be carbon dioxide is actually linear. Because 2 domains, even though they're double bonds, still just counts as 2. So it forms a perfectly straight line. Did I hit play, Matt?
Yeah.
Okay, thank you. The electron domain geometry is also linear. This and this will often be the same. This is only referring to the total number though. This one takes into account when it gets broken down into non-bonding. Once again, this is the main one we care about though. So, okay, questions on that one so far? Okay, hold up in the air your 3-sided little friend. Hold it up in the air for me. Okay, if you have something like that, you may have a smiley face, you're correct. And once again, as we're understanding Vesper, some people would do this. Once again, they want to get as far away as possible, right? That gets them a lot farther away than that one does right there. So, okay. Now, look at your little friend. Here's his name. Okay?
Trigonal plane.
Okay? So, I say it as trigonal planar. You can also say trigonal planar. Once again, fancy name, but look at him and it should make sense. Why are we using tri? Good. What does a plane mean? It's flat. He's 3-sided and he's flat. He, she, whatever. Right? So that's why it's called trigonal planar. Okay? 3 and 0. This is the same. What's my bond angle here? 120. So we got a circle cut into 3, right? let's see. An example of this one would be that guy. Now, once again, this is the difference between how we draw on Lewis versus what it really looks like. It's not wrong as a Lewis structure to draw it like this, because Lewis structures we typically draw left, right, up, and down. But what it really looks like is this. Questions on that one? Okay, take your little trigonal planar friend, okay? And what we're going to do is we're going to change one of those bonding pairs into a non-bonding pair. So it's still 3 domains, which means its domain geometry is still the same, because it still has 3 things. But the molecular geometry, how do we put it? Let's do this, ready? Take your little 3-sided friend and take off one of your blueberries, but leave the toothpick. A non-bonding pair of electrons still influences the shape, but we can't really see them in comparison to the molecules. So the way I think of them is they're kind of like a little ghost. They're pushing, but you can't see them. So all we're looking at here, can I borrow yours, Katie? Okay, is what do these 3 look like? We can't really see this toothpick, he's the ghost. But he's not just gone, because technically if he was gone, what shape would it be? Linear, right? He still influences the shape, we just can't see it. Okay, you ready for this technical name? That guy's name right there is bent.
What? That is hard.
Does it make sense though? Like, because it literally looks bent, right? Any guesses on what our bond angle is going to be?
120.
Why would you say 120 still?
120 and then 240. Because
Yes.
within
Oh, technically you just go the closest bond angle, Evan. But yes, I see what you're saying. Claire?
Well, there's still 3 bonds. Just one of them doesn't have like an atom or whatever, so or another atom. So they're all still like.
Good. So we're seeing like, right, there's still 3 things pushing. But here's the difference. A lone pair of electron has a greater repulsive force than a bonding pair does. And so it can push them a little bit closer together. So we just say it's going to be less than the 120. Okay, or like, let's see if I can build one here really quick. Right, so here's our 3-sided one. So this is normally 120. If this guy turns into a ghost, we can't see him, but he's going to push those a little closer together. So, yeah, Evan.
Wait, why does it push them a little bit closer together?
Because alone, let me draw an example here. So an example of, let's see, a bent one would be like this guy. The lone pair of electrons, because they're not contained in a bond, have a greater domain of space. They take up more area, I guess you could think, and so then they're just going to push those a little bit closer than when it's in a bond.
Okay.
Does that make sense?
Yeah.
Good question. Other questions on our bent structure? Okay, hold up your 4-sided friend.
Oh, this one. Alien spaceship.
Oh my lord.
Oh,
Alright, let's see if anyone has it. I think we're somewhere
God.
there. Okay.
Orange ball.
So some of you are not thinking outside of the paper and you built it like this. What's your bond angle of something like this?
90.
90 degrees. If you think more in 3D space and move them off of a single plane, you can make a structure that looks something like this. So the way I kind of visualize it is like a tripod with an antenna. So if you built something like this, you can have a smiley face. Which, if you notice, do you guys see how the bond angle here is definitely bigger than a straight 90? Yours might not be perfect because obviously it's Play-Doh and toothpicks, but if you do build this perfectly, look everyone, give me your eyes here for a sec. It is perfectly symmetrical. Like I can rotate it, right, and it looks exactly the same. So they're equally spaced as far away as they can be from each other. Okay, so 4 domains. The name of this structure is a tetrahedral. Going back to what does tetra mean? 4, yeah. 4 bonding, 0 non-bonding. The name is the same. This bond angle is not quite as like logical, but if you measure it out, it ends up being 109.5 degrees. Okay, and there's our example. Which once again, I can see why some of you built a T shape, because that's how we do it, like that plus sign shape, but you gotta translate it into 3D space. Questions on the tetrahedral? Okay, take your tetrahedral friend. If you don't have one made, make one real quick. Okay? And turn one of your sides into a ghost. Okay? So in a sense, I'm taking off my antenna, and I'm just left with the bottom half. Okay? Now, does this look similar to a shape we've already done?
Yeah.
What does it look like?
So it's like the trigonal.
Good, it's really close to that. So the name actually starts out with
It's gonna be trihedral.
Trigonal bend.
someone said last period too,
Oh.
which isn't bad logic. Because why would you say bent?
Well, so because of the ghost, it pushes them a little bit more, so they look bent as well.
Good, yeah, it's not flat though, like the planar, right? Does everyone see that? Right? If I put it on the table, it's not flat. Because that ghost is pushing them downward, right? So the name of it is it's called a trigonal pyramidal.
Oh my.
Because it's a 3-sided pyramid. Right? They're fancy, but they do make sense. At least some of them are fancy. Bent's not so fancy sounding, but. Sometimes I really feel like there are 2 committees who came up with these names. Because some of them are like really technical sounding and others are not. But
So other people were struggling.
I know. They're just like, let's just get out of here. Okay, questions on this one? Oh, bond angle is going to get less than again, so less than 109.5. And then this would be an example of one. Now, once again, here's the importance of the Lewis structure, everybody. Give me your eyes up here for a sec. Okay? You can get very off by just going from a formula and trying to tell me the geometry. Because the thing the formula doesn't show you are the ghost. But the ghost drastically influence the shape. Very often I've seen students just see this and be like, oh, well, there's 3 things, so it's going to be trigonal planar. It might be right, but you're taking your chances by not drawing the shape out. Okay? Okay, take your tetrahedral friend again. Now we're going to have 2 ghosts on him. Any guesses of the name?
Bigonal pyramidal.
What did you say,
Linear
Kimberly?
bend.
It's another bend.
Just bend.
Okay, because look, this was our bent before. Here's our other bent. What's the difference between our 2 bent shapes?
One
Or
is
ghost.
slightly more bent.
One is slightly more bent than the other. Yeah. The one with two ghosts is more bent than the one with one ghost, right? But they're still named the same. So the bond angle, the way we describe it, and this is going to seem a little weird, but it is a thing, is we're going to say it's less than less than.
What a guy. Evan's so smart.
Because we're just comparing things, right?
Evan should have a smiley face for that.
Did he say that?
Yeah, he said less than less than.
Evan, have a smiley face.
Yeah.
Water is a bent molecule.
So which one?
The double bent.
Less than less than.
Now, once again, this is even where Lewis structures can deceive you. Someone who doesn't understand chemistry would look at this and be like, oh, water's going to be linear. Why can't water be linear?
Because oxygen electronegative.
Not so much that's going to get to our polarity. It's really because of the ghost on it, right? The lone pairs force those things to bend away and not be a straight line. So,
Oh.
okay, questions so far? Okay, five-sided.
Oh no.
This is not gonna look good.
Yeah.
We need a bit more time to get this one together.
Well, I can explain to you that my shape is
Okay, hold up your five-sided friend for me. Let's see what we got.
He's doing his best.
No, it's like thirds, but like two.
It's like it's not like.
Okay, we're kind of there.
Okay, I need to put this here.
It's like thirds, but then the two.
It's like this. Is it like this? No, I bent it like the.
Yeah, I think you're there. You just flopped a little bit.
Oh, where did it go?
Okay, I'll let you be the judge of yourself, because I think most of us are kind of there. What you should have. Let's see here. Is something that looks like this.
Yes.
In a sense, you should have like two straight across from each other and then three in the middle.
Wait, so the one,
Okay,
wait,
so here's what it looks like.
the middle or
Okay, I love your guys' creativity, but when it's not time to build, we've got to take our hands off the Play-Doh, because I'm worried some of us are not learning these molecules because you're too distracted with building Play-Doh things. Sorry.
So are the electrons in the middle supposed to be like bent anyway, or are they like all?
They'll actually be straight because since there's some on the other side, they kind of prevent it from bending one way or the other.
Thank you.
So, yeah, good question, Carly. Okay, this guy right here, okay, is called, once again, think of its name because it really does make sense. It's just a little weird. Is it's called
Wait. Oh. They're just gonna.
okay, so break down its name. So trigonal means what? Or telling us what about it? 3. What does bi mean?
2.
2. So we have 2 3-sided pyramids.
Oh.
And in a sense, everyone, if you think of putting like walls on the side of it, that's what you'd end up with, is a pyramid, 2 pyramids stacked on top of each other. Does everyone see that?
Oh,
So trigonal bipyramidal. Okay.
yeah.
5 and 0. This is the same. Okay, what bond angles do we see?
We have 2 different.
Good, Zach. Which ones? What are they?
120 and something. And 90.
And 90. Yep.
There we go.
Yeah, good observation, Zach. So we have 2 different ones, right? So your middle one here, right? That's a 120. But then from top to side, there's your 90. So have a smiley face, Zach. Good observation. Questions on our trigonal bipyramidal? Okay, let's turn one of these into a ghost. Now here's the big question.
Will the ghost take the position of the top and bottom, or will it take a position of the ring?
Whichever
Top,
ones
top.
are closer.
Because it's the farthest.
Is it the farthest away?
Wait, no.
Where's the bigger bond angle?
In the middle.
On the ring, right? Because that's a 120 angle, right? So it's going to take the position of one of those. Okay, so I took mine off. This hole is the ghost still. Okay? Everyone look up here for a sec. So here's my molecule, right? Any guess of its name?
The teeter totter.
Teeter.
Close.
Oh,
There it is.
Wait, what?
It's called seesaw.
What?
Because I mean,
Donald Bipyramidal and the seesaw.
telling you, there had to be two groups of people, right? Bond angles get a little interesting in that we do have a lone pair up here that's repelling, but the more things you have to repel, the harder it is to repel them because these are also pushing away, right? So the bond angles for our 5 and 6s don't really decrease much because it's pushing, but it can't push these much closer. Pretty much, it's really hard for them to get less than 90. 90 seems, so the 90 stays put, the 120 gets a little less. Okay, 2 ghost. It's also going to take the position of one of the 120s. Okay. So now we have 2 ghosts, 3 bonding. Looks like this.
Oh. T-bow.
The T. T.
Wow.
They really like gave up halfway.
I wish they started earlier.
It would have been easier.
Man,
we get
why don't
seesaw
you-
and
What's my bond angle of my T-sheet?
90.
We don't have any more 120s, right? So. Now I'm hoping you're seeing like, the more you can visualize this in your head, the more they just make sense. And rather than having to memorize, I don't know how many different shapes we were talking about, they really do become quite logical if you can see them. All right, last one is 2 bonding, 3 non-bonding. So one more of these sides is going to turn to a ghost.
Bent. Oh no, linear.
There you go, Taylor. It's another linear.
Dang.
What?
They really gotta do us like this.
What's the difference between this linear and our first linear?
There are 3 non-bonded.
Yeah, this one has 3 ghosts, forcing it to be straight, right? While the other one just is the way it is. So, there you go. Okay, questions on 5-sided shapes. Okay, take a deep breath. Let's go to 6-sided.
Okay, wait, I need to fix this one really fast. I don't know what it's supposed to look like. I don't even remember what it's supposed to look like.
It's like a bubble with two ones.
Yeah, I don't know what mine
One of my circles gotta be so stupid.
Okay, hold up in the air your 6-sided friend.
Wait, my I'm worried.
Yes, I got it somewhat.
It's all.
Oh,
It's
I got it.
I like how many fingers you have to use.
Oh, it's nine.
Oh, there you go.
Okay, if you have, I think we're all kind of there. It's pretty similar actually looking to the trigonal bipyramidal, where you should have a top and a bottom, and then this time though a ring of 4.
Yeah.
So if you have something like that, give yourself a smiley face, you're correct.
Yeah, I'm not gonna touch that anymore. Kind of just.
Yeah, we out here getting 3 extra credit points on this.
That's a snake. Found out that we could do this. Wait, why doesn't it have
Now I can't spell. Octahedral.
OCTAHEDRA.
To write all of this. If I stop spelling halfway through. Okay, octahedral. Now I heard someone say, and I want someone to come up with the answer. Why would we call this shape an octahedral?
Oh, wait, that's the one. There are 8 angles.
Kinda. Or pretty much 8 sides, right? If you put walls on it again, you'd end up with an 8-sided diamond.
That would be really cool.
Why can't we just stay with electrons on the
I know, I kind of like. The other ones actually match too, where a tetrahedral is actually still 4-sided, but it does make it seem weird. Jump. Does everyone see that though? That's where they get the octahedral from. Bonding pairs 6 and 0. This would be the same. Bond angle is
90.
just 90s, right? 90 from the top, 90 in the middle, 90 all around. Okay. Let's take a ghost. So we got 5 and 1. Okay, so take one of your sides and turn it into a ghost. Yeah, technically doesn't matter what side because it's perfectly symmetrical. So here's what I get when I turn one of my sides into a ghost. Yeah, I can't really bend them much because they're already at a 90 degree, which seems to be the minimum bond angle that can exist. Okay? So this one is called
umbrella.
Square. A
Oh, that
square
makes
pyramid.
sense.
Wait, isn't a pyramid like?
That makes sense.
Oh,
Look,
the
nah.
base is a square.
Because the base is a square,
Okay, that
right?
makes sense.
And then if you bring them up to the sides, you get your square pyramid.
So what if it was like, let's see this one right here. So this base is a square and then it comes up.
Questions on our square pyramid here? Okay, let's get another ghost. So 4 and 2. Now the ghost is going to form as far away from the other ghost as possible, so it's going to take this top position.
No, it's like a T. An X. T.
Treasure map.
Any other guesses?
Word.
Cross.
Square. The square. Is that
Square
a-
something.
Squares.
Square.
No, oh, square pyramid.
Planar.
Okay, we have a spy fish. You're on the right track. Because it's flat, so it's square planar. Once again, bond angle doesn't really change because it can't. So.
Ooh, this is rough.
Okay, questions on that
For the
guy?
AP test, can we have Play-Doh?
You just bring some Play-Doh in with you.
Yeah,
I don't know if
but
it's
there's a
technically
ghost
not
here, a
allowed,
ghost
so
here.
just kidding. Okay, questions. Now, once again, this is where a formula can be very deceiving because a formula can only show you sometimes just what it's bonded to. It doesn't show you the non-bonding side of things. Okay, what I decided is, so there's 2 other things we're going to translate this into. We're going to learn about determining whether something's polar, and then what is known as its hybridization. I decided last period, after just going through these 6 shapes, though, that was enough knowledge shoved in you today. So we're going to hold off, and we're going to learn those other 2 things next time. Flip your notes, though, and there's a practice problem we're going to do some of to wrap up. So turn the page to practice problem 2.7.
Last time we didn't get, how would the
Oh, yeah, we had a little bit we didn't hit, huh?
Yeah.
Like we barely introduced resonance. Okay.
I had no clue.
Yeah, I was like, where's my footing? Can I fail?
I just
Okay.
left halfway.
So maybe we should reopen, like redo 2.6 again? Like
Yeah.
erase your scores and start a new one?
Oh, yeah.
Well, yeah, and there was a question that wasn't supposed to be there.
It was like asking about like.
Yeah.
Yeah.
Usually,
Yeah, sorry about that question. I don't know how that happened. Maybe we'll just round that. We'll just round everyone's quiz 2.6 up to 100%.
Yeah.
If you did it. Seem fair?
Well, I don't know if I ever turned it in.
Well, then turn it in today, and you'll get 100%.
Alright, sounds like
It's still open till midnight tonight, I think. Or maybe it was midnight yesterday. Well, I'll open it back up, and then you can do it. So, okay, so let's talk about.
Yeah.
Let's do this practice problem really quick, just to wrap this up, and then we'll go back and talk about resonance because we have time. Let's do this really quick though. Let's put all the Play-Doh back in the container. Say goodbye to your friends. And then make sure the lid gets on real tight so my Play-Doh doesn't dry out. I know, kind of by the end of the class period, huh?
It's too much surface.
Oh, you should just have Play-Doh on the desk for like the rest of the year. If we ever need like a little break.
I would if you could use it wisely.
Yeah, that's.
I mean, there's only one way that we can prove ourselves.
He does have a point.
That is true.
Be like kind of like your own like stress ball there, just like.
Yes.
Okay, once you get your Play-Doh away, flip to the page that has practice problem 2.7a. I'm going to draw them up here so that we talk about them.
I know we don't have to do this yet.
Wait, I'm concerned now. What's the next test?
Uh-oh.
Yeah, this is a shorter unit than Unit 1. We're pretty much done.
No.
We actually have to come into a fall break.
It's over.
It's like, I'll see you all on Thursday, right?
This is next on Wednesday.
She just says everyone come in Wednesday afternoon.
Oh, I would be so
That'd be smart.
Actually,
Oh, I see.
Okay, for these 4 structures, I want you to tell me their geometry and their bonding. Okay.
Geometry is the name.
The name, yep. Tell me its name and tell me its bond angles.
Okay. For 2.7a.
Alright, time to take a little step back. Austin, okay.
Where? Those? On the S axis.
Okay, this is the triangle.
Say that one more time.
Is there a line on the S?
Yes.
Wait, is the triangle?
I don't know what polar hybrid sound is.
What's hybridization?
So don't do the polarity or the hybridization column for now.
This is the 5.
Oh, this is the 5.
Yeah.
Wait, it's the.
It's seesaw.
Visualize it, right? Like see it in your head. See the 5-sided one, then turn one into a ghost.
Oh, seesaw. Seesaw. I'm gonna remember that one.
Visualize it. What does it look like?
90 degrees. I think it's got a couple.
And a 120, but a little bit small.
1, 2, 3, 4, 5, 6, 7, 8, square.
Yeah, just.
Oh, I just smeared my last letter all over my hand. Dang it.
The 5 and 6s are like.
That's just 90, right?
Yeah.
Okay, then this is 9.
Yeah, I would like try to do an outright.
Well, unmuted.
I tried. Okay, now. That's okay. Fail until you don't, Kimberly.
Wait, how do you call it?
Wait, but we didn't talk about that. Oh wait,
It's less than 180, right?
yeah.
And then those solstices, the one.
It's a little bit more bent than the triple.
Because I wouldn't be too far. We didn't talk about too far. Oh wait, no, because technically
That's forward, yeah. This is
four.
That would actually be really funny to watch. Like it would not be like just to watch that like someone reaches their hand there and everything.
4, 5, 6.
Now, so on your homework assignment tonight, everybody, on worksheet 2.7, there's columns that talk about polarity and hybridization. Just ignore those for now and just do the geometry one. Okay? I highly recommend that you try to do it as much as you can without your notes, because that's a great way to force your brain to start making these connections. But then, of course, if you get stuck, right, then look at your notes. Okay, let's check these real quick.
No.
Okay, 30 seconds.
No, but that's okay. Okay, so the base would be I have to draw it. Where's my
Yeah. Smiley face for each correct answer.
yeah. Smiley
Let's go.
It's like, yeah, I have a 30% in class. Put that baby up. You have like 130.
Wait and wait.
No.
Oh yes.
It would then, right? I believe so. Let me double check.
Okay, check your answers.
Yes. Oh, I spoke here, but
Questions?
I didn't put that in.
Okay. Okay, let's chat resonance really quick. Let me say this though, so in case the bell, we got about 5 minutes, so we're doing fine. If you want to leave your smiley faces with me today though, to put on first term, make sure you leave them with me before you walk out the door. If you're happy with your grade, then don't turn them in. If you're not sure because you're going to retake it today, like one of the tests, you could turn them in. If your grade is already an A, I won't put them in the computer. So if you're like, I might need them, but I might not need them, then I'd say turn them in,
Oh, okay.
just in case. If some of you are already at like a solid A, so there's no need for you to turn them in. But if there's a chance, I'd say turn them in.
What do you have?
Also, since it is the last day, I have just opened the correction retakes on Canvas. So I took away the passcode, but if you don't send me your corrections, I won't count your score. So you still have to send me your corrections. But just to save time, because it is the last day and I don't want to be having to check my email nonstop till 9 p.m. to send out passcodes, I've just unlocked them. Okay? Any other questions with end of term as we're wrapping that up?
Yeah.
Okay, did we talk about resonance at all last time?
A little bit.
Okay,
We started by talking about the ozone layer.
did we draw ozone?
Yeah.
Yeah.
Okay,
Oh, I remember that.
It sounds vaguely familiar. Oh yeah, the mirror.
This was ozone. I think I got that wrong. Oh, I didn't.
okay, so the idea of resonance, everybody, is this idea of how when a double bond, it only happens with double bonds, by the way. If something doesn't have a double bond, it's not going to resonate because there's nothing to move. When something has a double bond that can exist in multiple places and it still keeps everything balanced in terms of octets, that's the idea of resonance, where the actual structure is a perfect blend of the two. Okay, the way another example of resonance you can think of is it's kind of like how, like this is red paint and this is blue paint. So together it would be purple, and that's all you would see. Right? When you mix paint together, you don't see blue and red, blue and red, blue and red, like flickering. You just see purple. And that's all scientists see as well, as they just see this merged structure.
because the electrons are in constant motion that it seems like it's really in both places at once. And this is how you write your answer for resonance, is you show the possible structures with this arrow in between. I don't know what other things, I'm trying to think of what else I didn't say last time.
What's the exceptions to the octet
We
rule?
didn't go over exceptions to
Oh, okay. So exceptions to the octet rule. I drew actually one as an example, but there are some cases where you can get an odd number of electrons, which just end up making your picture look weird. So for example, nitrogen monoxide. And it just is like that because you ran out of electrons.
Homework, it was super weird. It was like with a noble gas. I was like, ew.
Yeah, so if you end up with an odd number, so see how nitrogen just has one random electron, you just stop because there's nothing else you can do. I don't bond again because oxygen is already full, so that's why it just kind of gets stuck. Once again, most of the exceptions will just happen. You'll finish your picture and probably be like, that looks weird. But if you followed all the rules, then it's just an exception to it. Another exception is you can have less than an octet. So boron trifluoride looks like this. And boron just has 6 around it. But if you think about it, why would boron typically look like this? How many valence electrons does it have?
3.
Only 3, right? Boron only has 3 to share anyways. And so that's just the way it is. And then we already talked about, but you can have things that have more than an octet, right? That have 10 or 12 or more around them, like PF5, right? Which we now know would be called a what shape? Like so. And then of course dots all around it. So. Okay, have a wonderful fall break. Let me know though if you do need more help with Lewis structures. And I'll see you guys in like a week and a little bit. You guys have like an extra long fall break now. Enjoy it.